Today, we will be debunking the possibility of the physics in the Fast and Furious 6 movie using our knowledge of conceptual physics. We will be looking at 3 unbelievable scenes from this movie. The first one being from when Dom heroically saves Letty while flying through the air.
As you can see in this scene, Dom, also known as Vin Diesel, jumps from his car using the car's momentum when he hits the wall to save Letty, also known as Michelle Rodriguez, in real life, midair. He saves her midair, then luckily lands on a windshield, but not completely breaking the windshield, just kind of cracking it, and then they both just walk away fine. We will be looking at both of their momentums and combined vectors in the air, along with their forces, to debunk the physics of this scene. First, a few key things to know. Dom weighs 102 kilograms, Letty weighs 54 kilograms, and both the car and the tank are going the same speed of 40 miles an hour.
Here's your girl. And your happy ending.
First, we have to convert the speed of the car and the tank to meters per second, which is done by dividing 40 by 2.24, and that gives you 17.88 meters per second for both the car and the tank. Now we can calculate the momentum for both Dom and Letty, which is momentum equals mass times velocity. So Dom's weight, which was 102 kilograms, times 17.88 meters per second gives us a momentum of 1,824 kilogram meters per second. For Letty, she weighs 54 kilograms times 17.88 meters per second equals 966 kilograms meters per second. Now, we can use the fact that they were traveling in a perpendicular path. We can use the parallelogram rule and find out the resultant. So Dom here was traveling this way, and Letty was traveling this way. And using Pythagorean theorem, we could determine this diagonal, or the resultant. So we did 1,824 squared plus 966 squared, and that equals 2,064 squared. So our resultant is 2,064 kilogram meters per second, which is their combined momentum after they made contact. So after that, we need to find out the force of them hitting the car as they land. So their combined weight is 102 plus 54 equals 156 kilograms. The velocity after the contact is then found by dividing their total momentum divided by their combined weight, and that gives us 13 meters per second. 13 meters per second times 2.24 equals 29.12 miles per hour. That's just to give you a reference of how fast they were actually going when they hit together. Now, their momentum was stopped in 0.6 seconds. We can use this to find the force of their impact, or the force that they caused. So we did 2,064 kilogram meters per second divided by 0.6 seconds to give us newtons, because newtons is kilogram meters per second squared. And that gives us newtons of 3,440 newtons of force that they impacted the windshield with. So using the math that we just did to get 3,440 newtons of force that Dom and Letty would cause on the windshield, they would go straight through that windshield, causing serious damage to the car and to both of them. But as you see in the movie, they just walk away and are completely fine, where instead they should be hospitalized and not be able to walk away like that.
For our next scene, we will be looking at a flying headbutt by Dom, who is also known as Vin Diesel in real life. He headbutts a thug on a plane in this scene, and in real life, that actor's name is Kim Cold. As estimated from the video, Dom jumps about 1.5 his body lengths and elevates himself into the air above Kim's body and headbutts Kim and tosses him back about 9 feet and knocks over a shelf and another man in about 2 seconds until he is at rest again. By using more specific information, we can figure out the force and acceleration of Vin Diesel to launch the Thug that far. So some basic information is that Dom, which is Vin Diesel, weighs 102 kilograms, and the Thug, who is Kim Cold, weighs 140 kilograms. So the Thug travels approximately 9 feet. Convert that to meters, that's 3 meters, and then we can use the formula velocity equals distance divided by time. So we're going to go 3 meters divided by 2 seconds, because that's the total time that the Thug had traveled through the air, and that equals 1.5 meters per second, which is the average velocity of the Thug. So then we're going to want to find the acceleration. So we go 1.5 meters per second divided by 1 second, which is 1.5 meters per second squared. That equals the acceleration. Then we can figure out the force by using the equation force equals mass times acceleration. We take the mass of the Thug, which is 140 kilograms, multiply that by the acceleration of the Thug, which equals 1.5 meters per second squared, and that equals 210 newtons. That is the amount of force needed to launch the Thug 9 feet in 2 seconds. And then we use that force and then divide it by 102 kilograms, which is Vin Diesel's weight, and that equals an acceleration of 2.06 meters per second squared. To create this sheer amount of force from somebody's neck is just completely absurd for a headbutt. In relation, you would have to toss a 7-kilogram bowling ball at an acceleration of 30 meters per second squared to apply that much force. That's just completely absurd, and nobody could apply that much force to another human being from their neck and head while jumping from a standing position. For our next scene, we'll be looking back at the first scene we did, but at a different scenario. We will be looking at the collision between the car falling off the bridge that stops the tank to a complete stop. We'll be looking at the vector quantities between the two that ended up in a complete stop.
Brian, that Mustang will make a nice anchor. Yeah, I'm on get rid of that car. Let it go take care of the cable. What's she doing? Okay, Toretto. Here you go. Now, your happy ending.
Some basic information about that scene is that the car is presumably a 1972 Mustang, which weighs 1,450 kilograms, and the tank is presumably an Abrams tank, which weighs about 54,430 kilograms. And also, we were assuming from our previous scene that we did, which is the same one, that the tank is traveling at 40 miles per hour, which is 64.37 kilometers per hour.
So, using the car's weight and the tank's weight, we are going to calculate each of their momentums. So first, here we will convert the tank speed, 40 miles per hour, to meters per second, which is 17.88 meters per second. Then we'll move on to the momentum because we already know its weight. So momentum is, again, momentum equals mass times velocity. The weight of the tank, or the mass of the tank, is 54,430 kilograms times 17.88 meters per second equals 973,208 kilogram meter per second for the momentum of the tank. And then the momentum of the car. First, we had to figure out the velocity of the car, and here we are assuming free fall. And watching the video, you can see that the car falls for a total of 5 seconds. So using the gravitational constant, or acceleration due to gravity constant, which is 10 meters per second squared, we're going to times that by 5 seconds, the amount of time it fell, to get 50 meters per second for the velocity of the car. And again, we already know the weight, or the mass of the car, so that's 1,450 kilograms times 50 meters per second equals 72,500 kilograms meters per second, and that is the momentum for the car. And then using the resultant again, we will subtract these two momentums to see the forward progress of the tank. So the tank momentum was 973,208 minus the car's momentum of 72,500 equals 900,708 kilograms meters per second. Using this, we can calculate the velocity of the tank after the impact of the car onto the bridge. So we use the new momentum of the tank of 900,708 kilograms meters per second, and we divide that by the weight of the tank, which is, again, 54,430 kilograms, and that equals 16.54 meters per second. To put that in perspective, that is 35.79 miles per hour.
So, as you can see from the calculations Jacob just made, that the scene in the movie is completely unrealistic. When the tank came to a complete stop, it just doesn't make sense, because it should have been going 35.79 miles per hour after the car had slowed it down just a little bit. So, from using our knowledge from conceptual physics, we have successfully debunked these three situations from Fast and Furious 6.